Hey everybody, this is Miss Darty. Today I want to go through, what we call VSEPR theory, and talk to you about how we determine the molecular geometry of a molecule. So you should have this chart. I highly recommend printing out this chart. It has another smaller chart on the bottom, but I highly recommend printing this chart out because you will be using this to determine your molecular geometries. There's no other way around it unless you memorize it, which I'm not requiring anybody to memorize these. So you need to have this chart printed out. So VSEPR, VSEPR, stands for valence shell electron pair repulsion. And the idea behind VSEPR, or valence shell electron pair repulsion, is that electrons have the same charge. They are all negative. And if you were to take physics, you would learn that like charges repel each other. So since electrons have all of the same charge, those electrons are going to repel each other. So valence electron pairs are going to repel each other and try to get as far away from each other as possible. And that is going to determine the molecular geometry or the shape of the molecule. And one last thing to know about VSEPR is that lone pairs, now by lone pairs I mean if you draw dots on the central atom, they are going to drastically affect your molecular geometry. So we go back to this chart, and the electron pair geometry column is not needed. It's just there. If you were to take general chemistry in college, you would use it. But the electron, I'm not going to worry about the electron pair geometry. What I'm worrying about is the VSEPR notation column and the molecular geometry column. What you are going to do, and what I'm going to take you through, is writing the VSEPR notation. And once you have the VSEPR notation written, you're going to match that up to the molecular geometry column. So, writing VSEPR notation, you see in the VSEPR notation side, you have A, B's, and E's. Well, A stands for the central atom. You always just have one A, because you can only have one central atom. B stands for the outer atoms. And E, be careful on E. A lot of people want to count dots, but E stands for electron pairs, or lone pairs of electrons on the central atom. Okay, again, E stands for pairs of electrons. And if you put a subscript after each letter, that number refers to how many of each thing you have. So writing VSEPR notation is a lot easier than it sounds. You always have to start with the Lewis structure though. So what I'm going to have you do is use the Lewis structures that you have already done and write the VSEPR notation from that. And so my examples that I'm going to do always starts with the Lewis structure and the Lewis structures that we did in the previous 3 videos. So always start with the Lewis structure, and then you write A, and you always have one A. And then you write B, and then you count the number of outer atoms and write that number as a subscript on B. And then you write E, and then count the number of lone pairs or dots, pairs of dots, on the central atom and write that number as a subscript on E. Now, determining the molecular geometry is very easy. Once you've written the VSEPR notation, all you have to do is locate your answer in the VSEPR notation column, and then match your answer to the molecular geometry column, which is the last column on the chart. So let's do a couple of examples. Well, actually, all of my examples. Okay. I guess CCl4, we won't worry about CCl4. Because it's the same. Oh, here we go. It just didn't get it. Okay. So, CCl4, what you're going to do is you are going to write A, and A stands for the central atom. So, A for the central atom, and then you're going to write B. And here, we need to count the number of outer atoms. So we have 1, 2, 3, 4 Cls. So this would be AB4. And then you check to see if your central atom, in this case the carbon, has any dots, pairs of dots on it. And here it doesn't. So the VSEPR notation is AB4. And then if you were to match that to your VSEPR theory chart, hang on. If you were to match that to your VSEPR theory chart, AB4 is right here, and it's tetrahedral. Okay, the next one we did was CH3Cl, and this goes into the idea that this is the number of bonded atoms. It doesn't matter what it is. So you write A, and then B, and then it doesn't matter what the element is. All you have to do is count the number of bonded atoms on the central atom. So we have 1, 2, 3 H's plus a Cl makes 4. So again, this would be tetrahedral. Next we've got NCl3. Now this is going to drastically, this lone pair of electrons is going to drastically affect the molecular geometry. So we've got A for the central atom, B stands for the bonded atoms, and we have 3 Cl's, so we have 3 bonded atoms attached to the end. And then we have a pair of dots. So here's where the E comes in. Now it is just one pair of dots, so it's just E. You could write the 1. I usually don't. But notice that it is pairs of dots and not the number of dots on the central atom, pairs of dots. So this this VSEPR notation is AB3E, and the molecular geometry, if you, again, use your table that you should have printed out, and this would be trigonal pyramidal. Okay, now this one's a complicated one. One of the very obscure shapes, I would say. I have to look up the shape, I don't have it memorized. But we have A, B. Here we have 1, 2, 3, 4, 5 F's, so it's going to be AB5. And we have a pair of electrons right there. So this is going to be AB5E. And if we were to look up our chart, AB5E is square pyramidal. Okay, moving on to the ClO3 example. We have A, B, we have 3 bonded atoms, and then we have a lone pair of electrons. So this would be AB3E, and this would be your trigonal pyramidal again. Okay, CO2 is next. Now, this goes into the idea that double bonds only count for 1. What you are doing is not counting the number of bonds. You are counting the number of bonded atoms, or in other words, the number of outer atoms. So here, you would have A, B, and again, you're just counting the number of outer atoms. So here we have 2 oxygens, so this would be AB2. We don't have a pair of dots on the carbon, so this is just AB2. So this would be linear. Okay, O3 is next. So here we have A, B, we have on the central oxygen, the middle oxygen, we have two bonded atoms on the central oxygen, and we have a lone pair of dots on the central atom. So this would be AB2E, which would be bent. Now, there are two different VSEPR notations for the bent molecule, and we will see that here in the next couple examples. Next is in O3. We have N is a central atom, so that's A. And then B, we have 3 oxygens attached, so that would be AB3. No electron pairs on the central atom, so this would just be AB3, which is trigonal planar. SiO2 is very similar to CO2. SiO2 would be A, B, 2, no E, which would be linear. Okay. This one, OBR2. So we have A, B, and we have 2 BRs, so that would be 2. And then E, we have 1 electron pair on the bottom and another electron pair on the top. So this would be AB2E2, which is the other version of a bent molecule. CO3 minus 2 is very similar to NO3 minus 1. We have a B3, no E, which is trigonal planar. And then last one, NBR3. We have A, B, 3 bonded atoms, and a lone pair of electrons, so this would be AB3, which is trigonal pyramidal. And so that's a VSEPR notation and molecular geometry. Thank you very much for learning with me today. I enjoyed learning with you.